Hello class, so today here in Mechanics of Deformable Bodies, we are now going to proceed to the second part of our discussion about shear and moment in beams. So for today's discussion, the learning outcomes are the following. Students must be able to construct shear and moment diagram using graphical or area method. And student must be able to locate maximum shear force and maximum bending moment in the shear and moment diagram. Okay, so previously in our discussion, we discussed the first solution in constructing shear and moment diagram, and that is by using shear and moment equations. Okay, but now class, no, we are now going to discuss our second solution. Okay, which is the graphical method. Okay, so graphical method class, this is also called area method. Okay, so this is our second solution, okay, for constructing shear and moment diagram. Okay, so in cases where a beam is subjected to several different loadings, determining shear and moment as functions of x and then plotting these equations can become quite tedious. Okay, so class, if a beam has many different loadings, okay, so what happens is that there will be more division of segments, right? So there will be a lot of segments, class, okay, if that's the case. Okay, and what happens, class, no, if you are going to use solution 1, we have to establish all of the equations, no, in each segment. Okay, so class, in this section, a simpler method for constructing the shear and moment diagrams is discussed. So this is a method based on two differential relations, one that exists between distributed load and shear, and the other between shear and moment. Okay, so class, for shear and distributed load, no, so this is the relationship. Okay, so we will no longer derive this relationship, ha? Okay, so we are going to use this relationship class. Okay, so it is said here, class, that the derivative, okay, of the shear equation, okay, with respect to x, that will be equal to W of x. So this W of x, class, this is the distributed load. Okay, and class, this derivative of shear equation with respect to x, this is actually the slope of shear diagram at each point. Okay, and this slope of shear diagram at each point, so this is actually equal to the distributed load intensity at each point. Okay, and also class, no, for shear and moment, this is the relationship. Okay, so the derivative of the moment equation, class, with respect to x is actually equal to shear. Okay, so this derivative of m with respect to x, this is actually the slope of moment diagram at each point. And this is equal to the shear at each point. Okay, so we are going to use these relationships, class, ha, in constructing shear and moment diagram, no, for solution 2, which is the graphical method. Okay, so we are going to consider here the sample problem number 6 that we solved in discussion 5.1. Okay, so for this beam class, okay, so class, for this beam, no, with these loadings, okay, so we already established, no, from the previous discussion, its shear and moment equations, no, at each segment. Okay, so here are the shear and moment equation, class, that we establish for each segment. So from 0 to 4, class. Okay, so this is the segment from 0 to 4. Okay, so class, the shear and moment equations here are the following. Okay, so V is equal to 30.1 minus 8x. This is for shear. And for moment, this is equal to 30.1x minus 4x squared. And also, class, for the segment from 4 to 7, okay, so this is the second segment. Okay, so the shear and moment equations, class, are as follows. Okay, so the shear equation is equal to negative 1.9. And the moment equation, this is equal to negative 1.9x plus 64. And lastly, class, for the third segment, that is from 7 to 10. Okay, so the shear and moment equations here are as follows. So the shear equation, this is V equal to negative 16.9, and for the moment equation, okay, so this is M is equal to negative 16.9x plus 169. Okay, so class, we're going to prove here, no, that the relationship that we discussed from the previous slide, no, is correct. Okay, so from here, class, no, it is said, no, in the previous slide that the derivative, okay, of the shear, okay, with respect to x, that is actually equal to the distributed load, okay, in that same segment. Okay, so let's say, class, for the first segment from 0 to 4, okay, so this is our shear equation. Okay, so if we are going to get, class, the derivative, okay, of this shear equation, okay, so the result must be, okay, the intensity, okay, of the loading here in this segment, which is 8. But in this case, the loading here, class, is downward, so it should be negative 8. No, so in this case, class, if you are going to derive, no, or get the derivative of this equation, or shear equation V, no, with respect to x, so this will be v over dx, so this will be equal to, class, what is the derivative of 30.1? Class, 30.1 is a constant, okay, and you learned that in your differential calculus, that the derivative of a constant is 0. So therefore, the derivative of 30.1 is 0. Now, what is the derivative of negative 8x? Okay, so class, for the derivative of negative 8x, you know that its derivative, class, with respect to x is negative 8. Okay, so from here, class, no, this proves, okay, that the relationship of the derivative of V, or shear of, or with respect to x, that is equal to the loading. No, so in this case, class, no, so this negative 8, this is actually the intensity, no, of the loading, and this is negative again because the loading here, class, is downward. Okay, so class, this proves, ha, that this relationship really works, ha. Okay, again, dv over dx is equal to w of x. Okay, and also, class, okay, we are also going to prove here that the relationship of moment and shear, that is derivative of moment equation, no, with respect to x, that is actually equal to the shear. Now, so from here, class, no, we are going to use this moment equation. Okay, so for this moment equation, class, okay, so solving for its derivative, so this will be derivative of the moment with respect to x. Okay, so this will be equal to, plus, what is the derivative of 30.1x with respect to x? So this is 30.1. Okay, and for the derivative of negative 4x squared, okay, so for its derivative, we will multiply this exponent, no, to 4, and then subtract 1, no, from 2, from this exponent, so that will become negative 8 times x. Okay, so this will be the derivative, ha, of the moment equation, okay, with respect to x. And class, if you are going to notice, okay, so if you can notice from here, class, this equation, 30.1 minus 8x, this is actually the shear equation, right? So we can say, class, that this is equal to the shear equation. Okay, so which proves, okay, that the relationship of moment and shear, that is dm over dx, is really equal to v. Okay. Okay. So from here, class, no, from this relationship, class, dv over dx equal to w of x. Okay, so we can also integrate this. Okay, so we can cross multiply this so that it will become dv is equal to w of x times dx. Okay, and from here, class, no, we can integrate both sides. And integrating both sides, class, okay, so we can cancel this integral sign and this derivative d, no? So what will remain here is just v, and then integral of w of x dx. Okay, so class, here, this integral of w of x dx. Okay, so this is actually a formula, okay, to solve for the area, okay, under this distributed load. Okay, so from here, class, now we can say that this shear, okay, or we can also call this as change in shear. Okay, so this is actually equal to the area under distributed loading. Okay, so instead, class, okay, so instead of establishing the shear equation first, okay, to solve for the shear at any point, we can actually just solve, class, no, the area under the distributed loading to solve for shear. Okay, so I'm going to demonstrate that, no, in our examples. Okay, so you have to take note of this, ha. Again, the shear or the change in shear, this is equal to the area under distributed loading. Okay, and in the same way, class, for moment, okay, so dm over dx equal to v. Okay, so class, we can cross multiply this dx here, no, so that it will become dm is equal to v times dx, no, and we will integrate both sides. So integrating both sides, this integral sign and this d will be cancelled. So what will remain here is m is equal to integral of v dx. And class, this integral of v dx, this is actually the a formula, no, for solving the area, okay, under, no, the shear diagram. Okay, so from here, class, now we can say that the moment, okay, or the change in moment, this is equal to the area under shear diagram. Okay, so class, instead of establishing moment equation, okay, to solve for the moment at a specific point, no, we can um, use, or we can just compute, no, the area of the shear, okay, the area of the shear from the shear diagram, okay, to solve for the moment. Okay, so take note, class, of this relationship, class. Okay, we are going to use this, no, in area method for constructing shear and moment diagram. Okay, so now let's discuss the procedure for graphical method or area method for constructing shear and moment diagram. So the first thing that we have to do, okay, so we have to compute first, no, the support reactions from the free body diagram of the entire structure. So this is actually the first step also, no, in our solution 1. Okay, so the second step, class, now we have to draw the load diagram of the beam, which is essentially a free body diagram, no, showing the values of the loads, including the support reactions. So use the sign conventions to determine the correct sign of each load. So class, we are going to use this sign convention, ha. So I've already mentioned this actually, no, in our previous discussion. But for loadings, class, let's say for concentrated load or force, okay, so it will be treated as positive, class, if the force or the concentrated load is upward, no, and if it's downward, class, it will be negative. Now for distributed load, okay, so this will be the same. If the distributed load is upward, that will be positive, and if it's downward, that will be negative. Now, class, for couple or moment, these are for um, couples and moments. So this is for plotting moments, no, in the moment diagram, class. So class, couple or moments that are clockwise, they are positive, okay, and for couples or moments that are counterclockwise, they will be negative. Okay, and also, class, no, for the sign convention, okay, in plotting the shear and moment, class. Okay, so class, if the shear is positive, so it should be plotted, no, above the x-axis. Okay, and if it's negative, class, it is plotted, class, below the x-axis. Okay, so that's actually the same, no, for moment. So if the moment is positive, it will be plotted at the or above the x-axis, and if it's negative, class, it will be plotted below, okay, the x-axis. Okay, so for the third step, class, working from left to right, construct the shear and moment diagrams for each segment of the beam by solving the area under distributed loading for shear and the area under shear diagram or under the shear diagram for moment. Okay, and for the last step, class, when you reach the right end of the beam, check to see whether the computed values of shear and moment are consistent with the end conditions. Okay, if they are not, you have made an error in the computations. Okay, so class, at first glance, using the area method may appear to be more cumbersome than plotting the shear and moment equations. However, with practice, you will find that area method is not only much faster, but also less susceptible to numerical errors because of the self-checking nature of the computations. Okay, so class, we are still going to use this relationship of loads, shear, and moment in constructing shear and moment diagrams using solution 2 or using graphical or area method. Okay, so class, if you're loading class, again, if it's a couple, okay, so the shear will just be a rectangle. Okay, and for its moment class, the moment class will just be triangle. Okay, and also class for concentrated loads. Okay, so the shear will also just be a rectangle, and also class for moment, the moment will just be triangle. Okay, and also class for uniformly distributed loads, okay, such as this and this. Okay, so their shear class will be triangles. Okay, and their moment class will be parabolic. Okay, and lastly class, if your loading is triangular, okay, so its shear class will be parabolic and its moment will be cubic. Okay, so take note of this class, ha. Okay, so to summarize that class, this is the sequence class, okay, of the geometry, of loadings, shear, and moment. So again, class, if your loading is a concentrated load, its shear will be rectangle, and its moment will be triangle. Okay, now, if your loading is rectangle class, so your shear will be triangle, and your moment will be parabolic. Now, if your loading class is triangle, so your shear class will be parabolic and your moment will be cubic. Okay? Okay, also class, we are going to use these rules, okay, for plotting the shear. Okay, so class, if your loading is negative constant, okay, so automatically class, its shear should be sloping down. Okay, and also class, if the loading class is negative increasing, so this is negative increasing, so class, the shear, it should be plotted concave down. Okay, concave downward. Okay, and if the loading class is negative decreasing, okay, so the shear, it should be plotted. Okay, it should be plotted concave upward. So this will just be easy to remember. Okay, so if the negative is increasing, that is sad. No, so that will be concave downward. Okay, but if the negative class is decreasing, so gradually it becomes positive, maybe. No, so if that's the case, class, so that will be happy. No, if the negative is decreasing, it will be happy. No, that's why it will be concave upward. Okay, so it will be easier, class, if you remember it that way. Okay, and also, class, if the shear, okay, if the shear class are sloping down, okay, so these are shears that are sloping down, so they are going down, from left to right. So this is sloping down, this is also sloping down, this is also sloping down. So for shears class that are sloping down, their moment, okay, since they are sloping down class, their moment should be sad, ha? So the moment class will be concave downward. It should be plotted concave downward, ha? Okay, and if the shear class, if it's sloping up, or if it's going up from left to right, okay, so these are shears that are sloping up. Okay, so this is sloping up, this is sloping up, this is sloping up, from left to right. Okay, so for this moment class, no, so this will be a happy moment, no, if the shear are sloping upward. Okay, so it will be a happy moment. Uh, Therefore, class, no, the moment should be concave upward. Okay, so they are concave upward. Okay, so again, class, take note, close of these relationships and rules, ha? Okay. Okay, so let's recall the formulas that we're going to frequently use here, no, in our discussion. Okay, so class, recall that the area, okay, of a triangle with base B and height h is equal to 1/2 base times height. Okay, and for parabolic spandrel, so class, parabolic spandrel has base B and height h. Okay, and class, instead of a straight line here as its hypotenuse, class, no, so we will have a curve here. Okay, so this curve, class, has an equation y is equal to kx squared. Okay, so this curve, class, is parabolic, no, or quadratic. Okay, so that means that, let's say for this variable x, no, it should be raised to 2. No, so that is ano, no, that is the nature of a parabolic or quadratic curve, right? So let's say for variable x, that is raised to 2. Okay, so class, the area of this parabolic spandrel, okay, so this is equal to 1/3 base times height. Okay, so actually, class, no, this formula came from the formula for general spandrel. So for general spandrel, class, this has base B and height h, and the, let's say, the equation, no, of the curve, class, is y is equal to kx raised to n. Okay, so class, the formula here is 1 over n plus 1 times b times height. Okay, so in this case, class, if n is equal to 2, okay, so we will just substitute 2 here. So this will become 1 over 2 plus 1, which is 1/3, right? So that is the formula, class, for parabolic spandrel. And also, class, no, take note here that this point, class, this point or this point, okay, so class, this is what you call the vertex. Okay, so this point, class, is called the vertex. And this point, class, it should be at the origin. Okay, it should be at 0, 0. No, this point. Okay, so class, let's say we put a line here. Let's say we create a line here. And then we consider this line, this curve, and then this line. Okay, so class, you might think that for that figure, okay, again, this line, this curve, and then this line. So you might think, class, no, that you can use this formula to solve for the area of that figure. Okay, 1/3 base, the base is this, and then the height is this. Class, you cannot do that. Okay, so you can only use this formula, class, no, if your parabolic spandrel, no, if its vertex here is at 0, 0. Okay, so class, in this case kasi, no, if we have here this line, and then this curve, no, so class, at this point, this is not the vertex. Okay, because this is not at 0, 0. No, this point is not at the origin or at 0. So therefore, we cannot use this formula. Okay, but class, on the other hand, let's say we put a line here. Okay, so we put a line here and then consider this line, this curve, and then this line. Okay, so class, for this figure, class, okay, we can solve its area using this formula. Why? Because, class, at this point, no, this is the vertex. No, and this point, class, is actually at 0, 0. No, so we can use, okay, again, we can use, no, this 1/3 BH. No, for the figure, if we consider this curve, the line here, and then the line, this line. Okay, since this point is at the vertex or at 0 or at the origin. Okay? Okay. So also, class, we are going to use this proportionality, no, frequently, no, in our problems here. Okay, so class, for triangle, okay, so let's say we have here this bigger triangle with base B and height h, and for this smaller triangle, with base x and then height y. So we can use this proportionality, that h over b, that is just equal to y over x. Okay? And also class, for parabolic spandrel, okay, so class, let's say for this larger parabolic spandrel, its base is b and its height is h. And for the smaller parabolic spandrel class, okay, so we have here base x and we have here height y. So we can use the proportionality h is equal to b squared is equal to y over x squared. Okay, so this is ano ha, the denominator here is squared. Okay, and these are the ano ha, the bases. Okay, and it cannot be b over h squared is equal to um, x over y squared ha. Okay, so the term here that is squared class are the bases, the base b and the base x. Okay, okay. Okay, so let's solve sample problem here. For sample problem number 1, draw the shear and moment diagram of the beam shown. Determine also the maximum shear force and maximum bending moment in the beam. Okay, so we are going to use graphical method or area method here, ha? Okay. Okay, so for this problem class, no, for our first step, of course, we have to solve the support reactions. Okay, so to do that, we have to draw first the free body diagram. Okay, so for the free body diagram of this beam class, since it is supported by a roller here, there will be one reaction here, which is R sub A. And here also class, this is supported by a hinge, so there will be a vertical reaction also here, so that will be R sub B. So the horizontal reaction here, again, it will just be 0 since there's no horizontal loadings no, in the beam. Okay, so here class, we are going to convert this distributed loading into its equivalent point load or concentrated load. So that will just be the area of this rectangular loading, which is 8, no, and then times 4. So 8 times 4, that is actually 32. Okay, and the position class of this concentrated load will just be at the mid-span, okay, of the loading, which is 2 meter here or 2 meter here. Okay, so from here, class, now we can solve for the reaction at A by taking moment at point B. So taking moment at point B, so that will be equal to 0. Okay, and then our assumption here is positive for clockwise moments. Okay, so RA class, so it will have a moment arm of 4 plus 3 plus 3, which is 10. So that will be positive since the rotation about point B is clockwise. Okay, now for the equivalent point load of the rectangular loading, which is 32 kilonewton. Okay, so its moment will be 32 times its moment arm, which is, this is 2 plus 3 plus 3. Okay, and it will be counterclockwise, no? Its rotation about point B, so it will be negative here. And also class, for this 15 kilonewton concentrated load, its moment will be 15 times its moment arm, which is 3 meter. And its rotation about point B will be counterclockwise. That's why it's negative here. So this will be equal to 0. So we can directly solve for R sub A. Okay, so R sub A class is 30.1 kilonewton. Now we can solve for the remaining reaction here, which is R sub B, using summation of forces vertical is equal to 0. So our assumption here is positive for upward forces. So this will be R sub A minus 32 minus 15 plus R sub B is equal to 0. So we just substitute the value of R sub A that we already solved. So this will become 30.1 minus 32 minus 15 plus R sub B is equal to 0. So solving for R sub B, so this is equal to 16.9 kilonewton. Okay, so from here, class, now we are now going to proceed to our next step. So we are going to solve the shear at every point. Okay, so from the from our beam class. Okay, so class, for this point, no, so we are going to ano ha, to solve the shear. Also for this point, we are going to solve the shear. Also for this point and for this point. No, so we are going to solve the shear, no, at every point, no, in each segment. okay, or the endpoints of the segment. Okay, so for the first segment class, the endpoints here are at this point and at this point. Okay, so we are going to solve for the shear. Okay, so class, at x is equal to 0, okay, so that will be at this point. Okay, so class, take note here, class, note that if at this point there is a reaction, okay, so this reaction, class, will just be the shear. Okay, so the shear at this point will just be equal to the reaction force here, okay, which is R sub A. Okay, so therefore, class, at x equal to 0, the shear force is the value of R sub A, which is 30.1. Okay, so that is the shear at x is equal to 0. Now, for the next point, that is at distance 4 meters, no, from the left. Okay, so at x is equal to 4, class, okay, we are going to solve for the shear. Okay, so we are going to use, no, the previous shear, which is 30.1. Okay, and then, class, for the loading here, okay, we are going to subtract, or we are going to sum up, okay, to sum up, class, this previous shear, okay, to the um, loading here. So, class, the loading here is a distributed loading, okay, and its area, class. Okay, so its area will be the change in shear. Okay, so class, we are going to, we can solve, no, the shear at x is equal to 4 at this point. Okay, by using, of course, the previous shear, that is 30.1, and we are going to sum this up, the area, okay, of this rectangular loading. Okay, and class, for sign convention, this is downward, so it will be negative here. Okay, so class, the area of the rectangular loading, that is actually 8 times 4, right? Base times height. No, so the height is 8 and then the base is 4. Okay, so 30.1 minus the area of the rectangular loading, which is 8 times 4, and that is 32, no? So, plus the shear here, okay, is negative 1.9 kilonewton. So, meaning to say, class, at this point, this is 4 meter, class, from the left. So, this is the x. Okay, so at this point, class, no, the shear is negative 1.9 kilonewton. Okay? Okay. So, after this, class, no, from this point, now we will proceed to this point. So, at x is equal to 7, we will also compute the shear. So, in this case, class, okay, so there is no loading here, no, at this segment. Okay, so that means to say, class, that uh, the previous shear, which is negative 1.9 kilonewton, no, that is the shear at 4, no, okay, at 4 meters from the left. Okay, so it will just be constant. Okay, from this point, class, 4 meters, okay, up to, okay, this point, which is 7 meters. Okay, so the shear here, class, will just be constant. Okay? Again, from this point up to this point. Now, class, no? At x is equal to 7, no? So, there is a constant shear here, which is negative 1.9. And as you can see here, class, okay, so there is a concentrated load here. Okay, so, class, for this concentrated load, class, so the shear, which is negative 1.9, so we will sum up this concentrated load. Okay, so for this concentrated load, class, for its sign convention, this is downward, so it will be negative. Okay, so this will be negative 1.9 minus the concentrated load. Okay, so solving this, class, so this will be negative 1.9 minus 15. Okay, so the shear here, class, is negative 16.9 kilonewton. So this is the shear, no, at x is equal to 7 at this point. Okay? Okay. So, after this, class, no, so the last point here will be here. So, this is x equal to 10. So, for x equal to 10, class, so class, here at this segment, okay, so the shear, no, at x equal to 7, class, is negative 16.9. Okay, so that will be constant, no, from 7, okay, to 10. From x equal to 7 to 10. Okay? So, this will be constant. Now, class, okay? So, meaning to say, class, the shear, okay, at x equal to 10 is negative 16.9 kilonewton. And class, you have to check this. Okay, since we are already here at the at the end, no, or at the end point of the beam, no, so we can check this shear. So class, this shear, no, so the numerical value of this shear class, it should be equal to the reaction at B. So in this case, class, no, there's a reaction here at the end point, which is the reaction at B. So the shear here, class, okay, it should be equal to that reaction. Okay? So, okay. So, class, in this case, class, no, we can say that this is, this is, naman, this is correct naman, because the shear here, class, is negative 16.9, and the reaction at B is 16.9. Okay, so we can say, class, that the shear, the values of the shear here, class, that we computed are correct naman. No? So, class, from here, we can plot this values now, in the shear diagram. Okay, so class, for the first value at x equal to 0, so this will be at this point. Okay, the shear here, class, is 30.1. So this is positive, so it will be plotted above the x-axis. Okay, so this is the x-axis, so this will be plotted above the x-axis. So this will be 30.1 kilonewton. Now, at x equal to 4, so at x equal to 4, this will be at this point. Okay, so at this point, class, the shear is negative 1.9. So negative, class, it will be plotted below the x-axis. That's why negative 1.9 is here. Okay, and also, class, no, since there is no loading nga here, okay, so from here to here, okay, from x, from 4 to 7, class, okay, the shear here will be constant. So this will be negative 1.9 half from here to here. Okay, so here, class, no, at this point, no, since there's a concentrated load here that is downward, so class, our shear, it will become negative 1.9 minus 15, no, and the value for that is negative 16.9. So negative 16.9 is somewhere here. So this is negative, so it will still be plotted below the x-axis. So this is negative 16.9, class, and since there's no loading here, class, so it will be constant here. Okay, so from this point up to this point, so this is negative 16.9 kilonewton. So class, this negative 16.9 kilonewton, so if you are going to sum up, no, the reaction here, which is 16.9, so that will become negative 16.9 plus 16.9. So this is positive, since this is upward. Okay, so negative 16.9 plus 16.9, class, that will be 0. Okay, so the shear diagram here, class, will go back to 0 here. Okay, so that, since that is negative 16.9 plus 16.9, okay, and that is our rule here, class. Okay, so class, the shear diagram, it should always, it should always close. Okay, that's why if the shear at this point, class, no, from here, if this is negative 16.9, okay, so the reaction here should be 16.9. Okay? So, you have to, you have to check that always. Because, class, if it doesn't close, okay, that means to say that, here, class, no, it did not go back, no, to the origin or to 0 here. Okay? So, that means that there's an error, no, in our computation for shear. Okay, so it's important, that it will close. It will be 0 here at this point. Okay, so class, this will now be, so okay, so class, our rule for connecting the points here, so let's say, for this point, which is 30.1, and for this point, which is negative 1.9. So class, since the loading here is rectangular, no, so our shear here will be triangle. Okay, so it will just be a straight line, no? So it will just be a straight line. Okay, and from here, class, there is no loading here. So, class, this will just be constant. So, this will just be a rectangle here. Okay, and also here, class. Okay, so for this point and this point, so we will just connect it this way because there's no loading here. So, the shear here will just be constant. No? So, this will just be a rectangle. Okay, so class, this will now be the shear diagram. Okay, now to solve class for the moment, no, to construct the moment diagram, we are going to use the shear diagram. So again, class, the area, okay, in the shear diagram, okay, so that will be the moment. Okay, so class, we are going to use the shear diagram here, ha? Okay, so let's say class, for this shear diagram, okay, so from this point up to this point, okay, so from this point up to this point, class, so this distance from this point to this point is x. Okay, so we are going to solve, no, the moment at this point. So that is at this distance x. Okay, so class, here, we have to solve first for this distance x because we don't know yet, no, this distance. Okay, so in this case, class, okay, so in this case, if this is x, okay, so let's say this distance, class, okay, so since this is 4 meters, so this distance, class, is 4 minus x. So again, 4 minus this x. Okay, so therefore, this distance, class, is 4 minus x. So class, here, we are going to use a proportionality um, for triangles. Okay, so as you can see here, class, we will have here two similar triangles. Okay, so as you can see here, no, there's a straight line here. Okay, so class, here, this bigger triangle, okay, so this is equal, this is similar, no, or proportional to this smaller triangle. Okay, so we will use proportionality here, ha, okay, to solve for this distance x. Okay, so from proportionality, class, okay, so by proportion, okay, so for the larger triangle, class, its height is 30.1. Okay, its height is 30.1 and its base is x. So therefore, this will become 30.1 over x. Okay, so this will be equal to the height over the base of the smaller triangle. So in this case, class, this is the smaller triangle. Okay, so class, the height of the smaller triangle, this is 1.9. So just disregard, no, the negative sign here. So we will just use the numerical value here, okay, of the height of this triangle. So the height of this triangle, class, is 1.9. Okay, so that will be 1.9. And then, plus the base here of the smaller triangle is 4 minus x. Okay, so therefore, class, 30.1 over x, this is equal to 1.9 over 4 minus x. Okay, so we can use any method, class, no, to solve for the value of x. So you can use your calculator or any solution that you uh, want to use, no. So this will be 30.1 over x equal to 1.9 over 4.1x. So class, actually, you can interchange um, this x, no, to you can put this into the numerator and this 30.1 to the denominator. Also here, you can interchange the numerator and the denominator here, ha. But class, if you're going to interchange, of course, this, no, the numerator and the denominator here, so you also have to interchange that here. Okay, so class, just to be ano, no, for the computation to be easier. So if you are going to use shift solve in your calculator, class, no, it's much better if you interchange the numerator and the denominator. So this will become x over 30.1 is equal to 4 minus x over 1.9. So if we just use shift solve here, class, so class, the value of x here is 3.7625. Okay, so this is the distance x, ha. So class, it has to be logical, ha. So since we use shift solve here, no, so you have to check if the value given by the calculator is logical. No, so in this case, class, this length is 4 meters. So of course, the distance x, it should be less than 4 meters. So in this case, class, this is logical naman. Okay, so plus if x equal to 3.7625, therefore 4 minus x is equal to 0.2375. 5. Okay, so from here, class, no, we are going to solve nga, no, the moment at this point. So, we know already that this distance, class, is 3.7625. Okay, so class, to solve for the moment at this point, okay, which is 3.7625, no, the distance. Okay, so class, to solve for the moment at this point, okay, of the beam, we are just going to solve for the area, okay, of this, or the area under this shear diagram. Okay, so we will just solve this area 1, okay, to solve for the moment, no, at this point. Okay, okay, so also class, now we have here this area 2. Okay, so this is the area of the smaller triangle. And then for this rectangle, class, this is area 3. And for this rectangle, class, this is area 4. Okay, so we are going to use these areas, class, okay, to solve for the moment. Okay, so we will start with the moment, okay, here at the starting point, no, from left to right. So here at this point, class, so this is x equal to 0 at this point. So class, obviously, the moment here is 0. Okay, so class, if let's say at this point, there's no applied couple or there's no a reaction moment, okay, at this point. So therefore, class, the moment at this point will just be 0. Okay, but class, if there's an applied couple here, or there is a moment reaction here, class, no, at this point, so there will be there will be a point that will be plotted in the moment diagram, ha? Okay, but since here, class, there's no applied couple, there's no applied moment, and there's no reaction moment here at this point, therefore, class, the moment here is 0, ha? Okay, so now, class, for the moment at this point, okay, so we will solve the moment at this point. So this is at x equal to 3.7625. So again, class, the moment at this point will just be the area, okay, of this, or the area under this shear diagram, which is the area 1. Okay, so the moment here, class, is just equal to the area 1. Okay, so class, for the area 1, so this is just a triangle, right? So this is just a triangle wherein the height is 30.1 and the base is x, which is 3.7625. So in this case, class, the moment here is just 1/2 times 30.1 times 3.7625. Okay, so therefore, class, the moment at x equal to 3.7625 at this point, class, ha? So this is equal to 56.626 kilonewton meter. And also, class, now we are going to use the sign convention pala here. Okay, so for its sign convention, class, the area here, class, no, is above the x-axis. So therefore, class, no, this area is positive. Okay, therefore, the moment here at this point, class, is positive. Okay, so this will be the area at this point. Okay, now proceeding to the next point. So this is the next point. So at this point, class, okay, at this point, the x here, class, is 4 meters. Okay, so our distance here, class, is 4 meters. Okay, so at this point, class, now we are going to, we can solve the moment here, class, no? Of course, we are going to use the previous moment, which is 56.626. So we will continue, no? And then sum up, no, the next area here. So in this case, class, no, the next area here, class, is this area 2. Okay, so for this area 2, class, so this is a triangle. Okay, so this is a triangle wherein the height here is 1.9 and then the base here, class, is 4 minus x, and that is equal to 0.2375. Okay, so the area here, class, will just be 1/2 base times height. But in this case, class, no, using sign convention, since this area is below the x-axis, so this will be negative here. Okay, that's why it will become 56.626 minus area 2. Okay, so again, the area 2, class, is just a triangle, so that will just be 1/2 base times height. So this will become 56.626 minus 1/2, 1.9, or times 1.9 times 0.2375. So therefore, class, the moment at x equal to 4 is 56.400 kilonewton meter. Okay, so from here, class, okay, so the next point, no, where we are going to solve the moment, class, is at this point. No, so this is 7 meters now from the left. So this will be at x equal to 7. So at x equal to 7, to solve for its moment, so we are going to use the previous moment, which is 56.4. And then we are going to sum up, no, this area. Okay? Since we are already at this point, ha? So the area here, class, at this segment is area 3. So class, this area 3, this is actually the area of the rectangle here. So this is a rectangle wherein the height is 1.9. Okay, and the base here, class, is 3 meters. Okay, so we are going to, um, okay, again, from the previous moment, that is 56.4, and then we are going to sum up this area 3, class. But since this is below the x-axis, so this will be negative here. Okay, so the area, class, of this rectangle is just base times height, so that will be 1.9 times 3. Okay, so therefore, class, the moment here is 50.7 kilonewton meter. Okay, so lastly, class, we are going to solve for the moment at this point. So this is already the end point, no, of the beam. So this is x equal to 10. So this is 10 meters from the left. So at x equal to 10, class, okay, so the moment here, class, okay, so using the previous moment, that is 50.7, and then we are going to sum up, no, the shear, no, at this segment. Okay, so the shear here, or the area here, class, no, at this segment is area 4, and the area 4, class, is a rectangle. Okay, so this rectangle, class, so its height is 16.9 and its base is 3 meters. So basically, class, the moment at x equal to 10, again from the previous moment, 50.700, and then, class, since the area 4 is below the x-axis, so this will be negative. Okay, so solving for this, class, no, so the area of this rectangle is just 16.9 times 3. So therefore, the moment here is 50.700 minus 16.9 times 3. So the moment here, class, is 0. Ayan. So class, here, no, at this point, which is x equal to 10, the moment here, class, should really be 0. Okay, why? Because here, at this point, there is no applied moment or couple. There's also no reaction moment. So therefore, class, the moment here at this point should really be 0. So, class, if this is not 0, okay, so there's something wrong in our computation. Okay, but since it is 0 here, class, so we can say that we computed the moment at each point correctly naman, no? Okay, so we are going to plot these values, class, no, in the moment diagram. Okay, so plotting the values of the moment at each point, no, from the previous slide. Okay, so again, at x equal to 0, the moment is 0. Okay, at x is equal to, the value of this is 3.7625, no, for this distance x. So the moment here at this point, class, is 56.626. So this will be plotted above the x-axis, no, this 56.626, since it is positive. And also, class, for x equal to 4, so that will be at this point. Okay, so at this point, class, okay, so the moment here, no, from the computed moment, no, at this point, that is 56.4. So it will go down a little bit, no, from 56.626. It will go down, so it will be plotted lower, no, than 56.626. So this will be here, at somewhere here. Okay, now at distance 7 meters from the left, so that is at this point. Okay, so class, the computed moment here is 50.7. Okay, so since this is a little bit lower, no, from these values, class, so it will be plotted a little bit lower also, no, so 50.7 is somewhere here. And class, the moment at distance 10 meters from the left, class, at this point, class, so we already computed that that is 0. So again, class, it has to be really 0. Okay, so the moment at the endpoints, which is at A and B, they should really be 0 because there is no moment reaction. or applied couple or moment at the end points, ha. So the moments here should really be 0. Now, class, to connect the points here, so let's say for this segment, okay, so we have here this point and this point. So class, to connect these 2 points, no, so from shear, class, so this is a triangle, right? So class, since the shear is triangle, the moment here, class, will be parabolic, right? So class, our rule here, if the shear is sloping down, so therefore class, our curve here should be sad, no? So it should be concave downward. That's why it's concave downward, ha? This is concave downward. Okay, and also class, no, for this segment from this point up to this point, so from this point up to this point, class, so it should be connected. Okay, so let's see first, no, the shear here. So at this segment, class, the shear is a triangle also, right? So class, we will connect it, or the moment here, class, it should be parabolic, no? So it will be parabolic. And here, class, since the shear here is sloping down, so the curve here should be sad, so that will be concave downward. That's why it's concave downward here, ha. Okay, although we cannot see it clearly since it's small here, no, but this is concave downward, ha. Okay, from this point to this point, so this is concave downward. Okay, and also class, no, from this point up to this point, so class, see here that the shear here, class, is a rectangle. Therefore, class, the moment here will just be a triangle. Okay, or it will just be a straight line that is sloping down. So this will be sloping down. Okay. Okay, so this will be sloping down because for this shear, class, so this is this is negative constant. Right? So this is negative constant since this is below the x-axis. No, so for negative constant, that is really sloping down, right? Okay, anyway, so also class, for this point, from this point up to this point, okay, so since this is a rectangle from the shear, no, so its moment will be a triangle. Okay, that's why it will just be a straight line. Okay, so this will now be the moment and shear diagram, class, for this problem. Okay, so the second part, class, we have to solve for, or to locate, no, from the shear and moment diagram, the maximum shear force for part 2, and for part 3, the maximum bending moment. Okay, so from the shear diagram, class, okay, so we are going to locate here the maximum shear. So the maximum shear here, class, obviously is this value. Okay, so this is 30.1. So this is the maximum shear. Okay, so this is 30.1 kilonewton. So class, for maximum shear and moment, no, so it is regardless, okay, if it's positive or negative. Okay, so the shear or moment that gives you the highest numerical value, okay, so that will be the maximum shear and bending moment. Okay, so in this case, class, no, the maximum shear is 30.1 kilonewton. Okay, now for the maximum bending moment, so we are going to locate that in the moment diagram, class. So from the moment diagram, the maximum bending moment here, class, is at this point. So at this point, class, this is 56.626. So therefore, this is the maximum moment. 56.626 kilonewton meter. So this will now be the answer. Okay, for sample problem number 2, we are going to draw the shear and moment diagram for the beam shown. And we are also going to determine the maximum shear force and maximum bending moment in the beam. Okay, so the given beam here, class, no, so this supports this distributed loading. Okay, so this is a rectangular loading. Okay, so the intensity of this loading is 15 kilonewton per meter. And its base, okay, or the length, okay, where it is acting, class, is 4 plus 3 plus 4. So that will be 11, no, 11 meters. Okay, so there's also a concentrated load here, 20 kilonewton. So this is 4 meters from here. And then 50 kilonewton. Okay, so this is also 4 meters from the other side naman, no? Okay, so from here, class, no, our first step is to solve the support reactions. Okay, so class, we will solve first, no, for the equivalent concentrated load of this distributed loading. So its equivalent point load is just the area of the rectangle. That is just 15 times 11. No? So that would be 15 times 11, and that is 165 kilonewton. Okay, so the location, okay, of this equivalent point load, class, is just at the at the center, okay, of the distributed loading, which is 5.5 meter, no? Since this is 11 meters, okay, so let's say from here to here, this is 5.5, and also from here to here, this is 5.5. Okay, so class, we are going to take moment at B, no, to solve for R sub A. So taking moment at B, so R sub A, class, its moment will be R sub A times 11. So it will be positive since it is clockwise, no, about point B. And then 20, this 20 kilonewton point load, class. Okay, so it will rotate, or it will have a moment 20 times its moment arm, which is 7 meters. And its rotation, class, about point D will be counterclockwise. So it will be negative here. Okay, now for the equivalent concentrated load, which is 165 kilonewton, its moment will be 165 times its moment arm, okay, about point D. So that will be 5.5. Okay, and this is counterclockwise, so it will be negative here. Now for the 50 kilonewton force, so its moment will be 50 times its moment arm, which is 4. And then its rotation about point B will be counterclockwise, so it will be negative here. So this will be equal to 0. So solving for R sub A, this is 113.41 kilonewton. Okay, so we can now solve for reaction at B, no, by summing up forces verticals equal to 0. So this will be R sub A minus 20 minus 165 minus 50 plus R sub B is equal to 0. So R sub A is 113.41. Now we just substitute that here. So solving for R sub B, so this is equal to 121.59 kilonewton. Okay, so after we solve for these reactions, we can now compute, no, the shear, no, at each point, no, of each segment, or the endpoints of each segment, no, here in the beam. Okay, so for the first point, that will be here. Okay, so this is at x equal to 0. Okay, so the shear here, class, again, class, the shear here should be equal, no, to the reaction here. Okay, since there's a reaction here at this point. Okay, so therefore, class, the shear at x equal to 0 is just equal to the R sub A, or the reaction at that point, no? So therefore, the shear here is 113.41. So this is R sub A, ha? So this is 113.41 kilonewton. Okay. So class, we are going to solve next, no, the shear at this point. Okay, so take note, class, ha, that the original loading, no, we are going to for shear, okay, for shear, the loading that we are going to use should be the original loadings. Okay, so just because we convert this distributed loading into its equivalent point load doesn't mean that we can use this, ha, in solving for shear. No, we have to use the original loading, okay, which is a distributed loading. Okay, so again, class, we are now going to proceed at this point. So this point, class, is at x equal to 4 meters. So at this point, class, the shear, okay, it will just be, of course, the previous shear. Okay, and then we're going to sum this up, no, to the area under the distributed loading here. Okay, so in this case, class, the shear here will be 113.41. Okay, so plus for this distributed loading, so this is downward, so this will be negative here. And its area, class, will be 15. Okay, 15 times its base, which is 4. Okay, so that will be 15 times 4. So this is the area, okay, of the rectangular loading, ha, at this segment. Okay, so since we are considering the shear at this point. Okay, so the shear here, therefore, class, is 53.41 kilonewton. Okay, so this will be the shear at this point. But class, here at this point, there is a concentrated load that is downward. Okay, so therefore, class, no, the shear here, class, at this point, no, will become equal to 53.41, and then we sum up this concentrated load. So this is downward. So for our sign convention, this is negative. So this will become 53.41 minus 20. So the shear here, class, will become 33.41 kilonewton. Okay, so from here, class, we are now going to proceed to another point. So at this point, so this is 7 meters from the left, no? So at x is equal to 7. Okay, so the shear here, class, will be the previous shear, okay? And then we're going to sum up, no, the loading in this segment. Okay, so in this case, class, the segment, the loading here, okay, so this is 3 meters, and then again, the height is 15, okay, kilonewton per meter. So the shear at x equal to 7 at this point, class, so that will be the previous shear, which is 33.41. Okay, so class, these loadings, again, these are, these are downward, so this will be negative. So the area, class, of this loading at this segment, so this is 15 times 3. Okay, so that will become 33.41 minus 15 times 3. So therefore, the shear here, class, is negative 11.59 kilonewton. Okay, so this is now the shear at this point. Okay, x equal to 7. Now, also, class, no, at this point, there is a 50 kilonewton concentrated load. Okay, so this shear, class, so we will sum up, no, this concentrated load. So in this case, class, this is downward, so this will be negative also here. Okay, so the shear here, class, at this point, therefore, will become negative 11.59 minus 50. So this will be negative 61.59 kilonewton. Okay, so from here, class, from this point, so we will now proceed at the last point. So this is x equal to 11, no? 11 meters. So at x equal to 11. So this is 11, class. Okay, so this is 11. At x equal to 11, class. Okay, so from the previous year, that is negative 61.59. And then we are going to sum up, no, this loading, no, at this segment. So at this segment, class, no, the loading here is 4 meters, no, and then 15 kilonewton per meter. That is the height. Okay, so this is downward. So this will be negative here. So this will become negative 61.59 minus 15 times 4. So therefore, class, the shear at x equal to 11. Again, class, this is x equal to 11, ha? So this is typo error. Okay, so the shear here, class, is negative 121.59 kilonewton. And you can check this, class, no, since we are already at the end point. So, class, the shear here, okay, so if you sum up, class, the reaction at this point, that is R sub B, it should be 0. Okay, so in this case, class, okay, so negative 121.59. So the reaction here is downward, therefore it will be positive. So negative 121.59 plus 121.59, it will become 0, right? So therefore, class, we can say that our computation for shear is correct. Okay, since numerically, no, the shear here, okay, and the reaction are equal. Okay, so therefore we can say that our computation for shear is correct. Okay. Okay, so from here, class, no, we can now plot, no, the values of this shear, no, at each point. So class, at x equal to 0, again, the shear is 113.41. Okay, so we are going to plot that. So this is positive, so it will be above the x-axis. So it will be plotted here. And then for the shear here at x equal to 4, okay, at this point, plus the shear is 53.41. Okay, so 53.41 is somewhere here. Okay, and then at this same point, class, Okay, so since there is a concentrated load here, class, so this will be subtracted by 20. Okay, so this will go down 33.41. So this will be the shear here also. And then at x equal to 7, so at this point, class, the shear is negative 11.59. So since this is negative, class, so this will be plotted below the x-axis. So this will be plotted somewhere here, no, negative 11.59. Okay, and also, class, there's a concentrated load here. Therefore, this shear will go down further. So this will become negative 61.59, class, no, at this point. So this will be at this point, no, negative 61.59. And lastly, class, no, at the shear, or for the shear at the endpoint, so that will be x equal to 11. Class, the shear here is negative 121.59. Again, class, this is just typo error, ha? This is x equal to 11. Okay, so this will be somewhere here, negative 121.59. Okay, so class, connecting this points, okay, so let's say from this point to this point, okay, so since the loading here is just rectangle, so definitely the shear will just be a triangle, no? So it will just be a straight line. So we will just connect these 2 points, no, by a straight line. Okay, so it will go down. And then for this point and this point, so class, again, the loading here is a rectangle. So we will just also connect this, okay, by a straight line. Okay, so it will form a triangle, no? Okay, so class also, so this will go down here. And then here also, class, rectangle. The loading here is rectangle. So the shear will just be triangle, no? So it will just be straight line here. Okay, and also, class, okay, this is negative 121.59. So if we are going to add this reaction force, since this is upward, no? So this will be 0. So our graph here, class, will close here, ha? It should be close. Okay, so it should go back to 0 here. Okay, so this will now be the shear diagram. Okay, so from the shear diagram, class, no, so we are going to use this, no, to solve for the moment, no, at each point. Okay, so here, class, no, we can see that this is a trapezoid, no, at this area. Okay, so class, the triangle here, so we can divide this kasi, no, into triangle and into rectangle. So this triangle, class, so this will be the area 1. And then this rectangle, so this will be the area 2. And then we have here this triangle, so this will be the area 3. And then we also have this smaller triangle, so this will be area 4. And we have this rectangle, class, this will be area 5. And this triangle, so this will be area 6. Okay, so class, notice here that here, class, okay, so there will the shear here. Okay, so the shear here, class, will pass through the x-axis na at this point. So class, this distance from this point up to this point where the graph passes through the x-axis, class, we don't know this distance. So let's say this is distance x. Okay, and class, if this is distance x, no, so this remaining distance, okay, since this is 3 meters, so 3 meters minus x will be this distance. So this is 3 minus x. Okay, so class, as you can see here, there will be a larger triangle here, so this triangle, and this will be similar, or this is similar to this smaller triangle. Okay, so we can use proportion here, class, to solve for x. Okay, so it will just be the height of the larger triangle over its base, and then equal to the height of the smaller triangle over its base. Okay, so in this case, class, the height of the larger triangle, this is 33.41. So it will be 33.41 over its base, which is x, equal to, okay, the height of the smaller triangle. So this is 11.59. Okay, so disregard the negative sign here, class, ha? Okay, so we will just use the numerical value, which is 11.59, over the base. So the base here, class, is 3 minus x. Okay, so we can solve for x using shift solve. Okay, so we can interchange the numerator and the denominator. So we can use, so that the calculator can easily give the answer, no? So we can say that x over 33.41, that is equal to 3 minus x over 11.59. Okay, so solving for x, class, so that will be 2.2273. Okay, so this x, this is the this is the value for this x, 2.2273. So again, class, you have to check if this is logical. Okay, if the answer that the calculator gave, okay, is logical. So in this case, class, the length here is 3 meters. So obviously, this distance x, it should be less than 3 meters. So in this case, class, this is less than 3 meters naman, no? So we can say that this is logical. Okay, so if x equal to 2.2273, therefore, 3 minus x will be 0.77267. Okay. So from here, class, now we can now start solving for the moment at each point, no, of the segment in the beam. Okay, so we will start with x equal to 0. So that will be at this point. So again, at this point, class, the moment is 0 because there is no applied couple, there is no applied moment, and there's also no reaction moment here. So therefore, the moment here, class, will just be 0. Okay, and then after this, class, no, at this point, so this is at x equal to 4 meters. Okay, so class, the area at this segment, no, in the shear diagram, class, so this will be the moment at this point. Okay, so in this case, class, we have here the area 1 and the area 2. And class, using sign convention, these areas are above the x-axis. Therefore, this will be positive. Area 1 plus area 2. Okay, so for area 1, class, this is a triangle. Okay, so the height of this triangle, class, is 113.41 minus 53.41. That is the height, ha? So this 113.41, this is the height from here to here. Okay, so the height that we need is just this height. So therefore, this is 113.41 minus 53.41. Okay, and its base is 4 meters. And for this rectangle, class, this is the area 2. The base here, class, is 4 meters. And then its height is 53.41 kilonewton. Okay, so solving for the moment, class, so that will be the area of the triangle. So that will be 1/2 113.41 minus 53.41 times 4 plus the area 2, which is a rectangle. So that will be base times height. So that will just be 53.41 times 4. So solving this, class, so the moment, therefore, at x equal to 4 is 333.64 kilonewton meter. Okay, so this will be the moment at this point, ha, of the beam. Okay, now, we are going to solve next, no, for the moment at this point. Okay, so at this point, class, the moment here, okay, so the distance here first, class, is 4 meters plus x. Okay, so the value of x, class, is 2.2273, ha. Okay, so therefore, at this point, no, the distance, no, from the left is 6.2273. That is just 4 meters plus 2.2273. Okay, so that will be at this point. Okay, so at this point, class, the moment will just be the previous moment, which is 333.64. Okay, and then we sum up, no, the area here, no, so this is area 3. Okay, and since this is still above the x-axis, so this will still be positive, ha, this area 3. Okay, so the moment at this point, class, okay, will be 333.64 plus the area 3. And this area 3, class, this is a triangle wherein its height is 33.41. Okay, and its base is 2.2273. So the area 3 here, class, will just be 1/2 33.41 times 2.2273. 1/2 base times height, no? So the moment here, class, will be 333.64 plus 1 half times 33.41 times 2.2273. Okay, so the moment at this point, class, is 370.85 kilonewton meter. Okay, so class, the next moment, class, will be at this point. Okay, that will be at this point. No? So this point is 4 plus 3 meters. Okay, from the left, 4 plus 3. So this will be at x equal to 7 meters. Okay, so class, the moment here will be the previous moment. Okay, and then we are going to sum up this area. Okay, so this area, class, is area 4. Okay, so this is a triangle. So this will just be 1 half base times height, wherein its height is this. So this is 11.59. And this base is 3 minus x. That is 0.77267. Ha? Okay, so the moment, therefore, at x equal to 7, that will be 370.85 minus area 4. So the area 4, 1 half base times height. So that will be 1 half 11.59 times 0.77267. So solving for the moment, class, at x equal to 7, that will be 366.37 kilonewton meter. Okay, so lastly, class, we are going to solve the moment at the end point. So this is x equal to 10. No, this is 11. This is 11 meters, right? 4 plus 3 plus 4. So this is 11, class, ha? So this is at x equal to 11 meters. So this is typo error. Okay, so at x equal to 11 meters, class, so that will just be 300, or the previous moment, which is 366.37. Okay, and we are going to sum up here, no, these areas. So class, these areas, these are below the x-axis. So therefore, the sign convention here will be negative. So area 5 will be negative here, and then area 6 will be negative here. So class, area 5, okay, for area 5, class, this is a rectangle. Okay, so this is a rectangle, so its area is just base times height, wherein its base is 4 meters and its height is 61.59. Okay, so that is its height. Okay, and for area 6, class, so this is a triangle. Okay, so triangle, 1 half base times height. Its base is 4 meters and its height is this height. So this height, class, is 121.59 minus this, which is 61.59. Okay, so this is the height, okay, of the triangle. Okay, so solving this, class, so this will become 366.37 minus area 5, which is 61.59 times 4, minus the area 6, which is 1 half times 121.59 minus 61.59 times 4. So the moment here, class, will be 0. Okay, so again, class, this is at x equal to 11, ha? Okay, so this is just typo error. This is x equal to 11. So the moment here is 0. So again, class, no, so this is the point, no, or the at this endpoint, class. Okay, the moment here, class, should be 0 since there's no applied couple or moment here and there's no reaction moment here, ha? So the moment really here at x equal to 11 should be 0. Okay, so we are going to plot these values, class, of moment in the moment diagram. Okay, so plotting the values of moments that we computed in the moment diagram. So this will be for the moment diagram, no? So starting here at this point. So at this point, class, the moment is 0. Okay, so the moment is 0 here. Okay, so at this point, class, which is, this is 4 meters now from the left. The moment here, class, is 333.64. And then at x is equal to 6 point, this is, what's this, distance? Okay. So at this distance, this is 4 plus, 2.2273. So at this point, so this is 6.2273 from the left at this point, no? So at this point, class, the moment that we computed is 370.85. So it will be here. Okay, so these moments, class, no, these first two moments, these are positive, so it will be plotted above the x-axis, ha? Okay, now for the next point, so the next point is here. So this is 7 meters from the left. So at x equal to 7, class, no, the computed moment is 366.37. And at this point, so this is x at x equal to 11, no, so the moment here, class, is 0, no. So class, connecting this point, so we are going to use our rule. Okay, so from this point up to this point, okay, so class, here our shear, okay, this is like a triangle, no, so this is a triangle here. Okay, so since this is a triangle here, class, so the moment here will be parabolic. Okay, so class, the shear here is sloping down. So therefore, our curve here should be concave downward. That's why it's concave downward. Ha? So this is concave downward. Okay, and then afterwards, from this point up to this point, okay, so class, the shear here is a triangle. Therefore, the curve here, class, will be parabolic. The moment here will be parabolic. Okay, and since the shear is sloping down, okay, so the curve here, class, okay, the parabolic curve here, class, should be concave downward. Okay, also here, class, the shear here is a triangle, so the moment here, class, should be parabolic. Okay, and since the shear is sloping down, so the curve should be concave downward. Okay. Also, class, here, from this point up to this point, so this is also a triangle here, the shear. Okay. So, the moment here should be parabolic. Okay. And the shear here, class, is sloping down. So, the moment here should be concave downward. That's why it's concave downward here, ha? Okay. So, from here, class, now we can now locate, no, the maximum shear, okay, and the maximum bending moment. Okay, so this is already the shear and moment diagrams, ha? Okay, so for the second part, that is for the maximum shear. So from the shear diagram, class, as we can see here, the maximum shear is here. Okay, so this is a negative value. But again, class, we are going to disregard, okay, the sign, if it's positive or negative, ha? So what's important will be the maximum numerical value. So, therefore, class, the maximum shear here is negative 121.59 kilonewton. Okay, now for the third part, that will be for the maximum bending moment. So, from the moment diagram, class, obviously, as we can see here, the maximum moment will be at this point. So, the maximum moment here, class, is 370.85 kilonewton meter. So, this will now be the answers for this problem. Okay, so for the third sample problem, we are going to draw the shear and moment diagram, okay, of this beam. Okay, so we are also going to determine the shear force and the maximum bending moment in the beam. Okay. Okay, so for this problem, class, we are going to um, compute first, no, the support reactions. Okay, so class, we are just going to, to compute first the equivalent point load of this distributed loading. So its equivalent point load will just be the area of this rectangle. So this will be 100. Okay, so the height is 100 times its base, which is 2 plus 4, that is 6. So 100 times 6. So the equivalent point load here, class, will be 600 pounds. Okay, and its location, class, okay, it will be at the mid-span, okay, of the loading. So if the loading is 2 plus 4, so that is 6. No, so this equivalent point load, class, will be located 3 meters from here. So this is 3 meters. This is also 3 meters from here. Okay, okay, so that's the location of the point load. Okay, so from here, class, now we can take moment at point B, okay, to solve for R sub A. So taking moment at point B, so the moment of RA is RA times its moment arm, which is 4 plus 1 plus 1, which is 6. And it will be positive since it is clockwise about point B. Now, for this equivalent point load, its moment will be 600 times its moment arm. So, this is 3 plus 1 plus 1. Okay, and its rotation will be counterclockwise about point B. So, that will be negative here. And plus also, there's an applied couple here. This is 1,200 pound-feet. Okay, and this is clockwise. So if we include that in our summation, so that will be positive, no, 1,200. Okay, so this will be equal to 0. So solving for R sub A, that will be 300 pound. Okay, so we can now solve for R sub B also by using summation of forces verticals equal to 0. So this will be R sub A minus 600 plus R sub B is equal to 0. So R sub A is 300, no? So we can solve for R sub B, and that is also 300 pound. Okay, so from here, class, now we can now start solving, no, for the shear, no, at each point, at each segment, no, in the beam. Okay, so we will start at x equal to 0. Okay, so that will be at this point. No, so again, class, how we are going to use the beam. Okay, the beam loading. Okay, wherein the loadings here are the original given loadings. Okay, so again, class, just because we computed the equivalent point load here doesn't mean that we can use this half for the shear diagram. No, we have to use the original loadings, ha. Okay, so at x equal to 0, class, obviously, no, at this point, there is no reaction force here. So, class, the shear here will just be 0. Okay, since there is no reaction force here. Okay. Okay, so proceeding to the next point. So the next point, class, is here. So here, this is at x equal to 2. Okay, so at x equal to 2, class. Okay, so the shear here, okay, will just be the area of the distributed loading in this segment. Okay, so the area, class, of this distributed loading at this segment is just 100 times 2. Okay, so that will be the shear. And since the loading is downward, so it will be negative, ha. So the shear here, class, will be negative 200 pound. But class, here at x equal to 2, there's also an upward, no? There's an upward reaction force here. Okay, so the shear here will become negative 200 plus this reaction force. So this is upward, no? So it will be positive here. Okay, so the shear will become negative 200. So class, the reaction at A is 300. So the shear here will become negative 200 plus 300. And that is 100 pound. Okay, now for the next point, that will be at this point. Okay, so at this point, class, this is 2 plus 4, no? So that will be 6 feet, no, from the left. So at x equal to 6, okay, the shear here will be the previous shear, okay, minus the loading at this segment, or the area, no, of the loading at this segment. So in this case, class, the area, no, of the loading at this segment is 4 times 100. Okay, so the shear here will be, again, from the previous shear, that is 100, minus, so this will be negative since the loading here is downward. So this will be negative 100 times 4. So therefore, the shear here at this point, this is x equal to 6, no? So the shear here is negative 300 pound. Okay, and also, class, here, class, no? So there's a couple here, no? So the shear here will just be, will just be constant. Okay, so since this is a moment, no, so there's no effect, no, for shear. Okay, so from here, okay, to from ano ba itong length na to? From 6, no? From 6 to 8. Okay, so the shear will be constant. Okay, so at x equal to 8, so that will be at this point, no? So at x equal to 8, that will, the shear here will just be negative 300, ha. Okay, so again, class, because there's no loading here. Okay, so this applied couple here, it will have no effect to the shear because this is a moment. Okay, so class, here, the shear at x equal to 8, so that will be at this point. So this is negative 300 pound. And you can check if it's correct, no, by checking the value class of the reaction force here, okay, at this same point. Okay, so since the shear here is negative 300 pounds, so class, the reaction here should be positive 300. Okay, so in this case, class, this is correct, no? So we can say that our computation for shear is correct. Okay, since when we sum up this shear at this point, so this is negative 300, to the reaction that will be plus 300, negative 300 plus 300 is 0. So therefore, okay, again, our computation for shear, we can say that it's correct. Okay, so class, we are going to plot these values of shear, okay, in the shear diagram. Okay, so for the first point at x equal to 0, class, the shear is 0. Okay, so this will be here. And then at x equal to 2, at this point, the shear is negative 200. So negative 200, it will be plotted below the x-axis, ha? So negative 200 will be here. And then at this same point, class, since there's a 300 concentrated upward force here, class, okay, so it will go up. Okay, so the value of shear here is 100, no? So that is positive, so it will be plotted above the x-axis. That's why 100 pound is here. Okay, and then at the next point, that will be at this point. Okay, so this is at x equal to 6, plus the shear here is negative 300. So negative 300, so it will be plotted below the x-axis. So negative 300 is somewhere here. Okay, and class, at x equal to 8, the shear is negative 300. No? So this shear will just be constant here, ha? Okay, since there's no loading here, ha? There's no concentrated load, there's no distributed load, no? Okay, so again, this applied couple, it will have no effect to the shear. Okay, so this will be constant from here to here. Okay, so class, to connect the points here, okay, let's say for this point up to this point, since the loading here is a rectangle, no, so the shear will just be a triangle, so it will just be a straight line here. Okay, it will just be connected by a straight line. Okay, and then going up, and then for this point and this point, okay, so again, class, the loading here is rectangle, no? So the shear will just be a triangle, so it should be just a straight line, no? So these 2 points, class, they will just be connected now by a straight line. And then it will just be constant here, so it will just be connected by a straight line also here. Okay, so class, again, this should close, ha? The shear diagram should close. So since this is negative 300 and the reaction force here, class, is positive 300, no? So it will close here. It will go back here at 0. So this is correct. Now we can say, okay. So this will now be the shear diagram. Okay, so from the shear diagram, class, okay, so for the moment, class, now we are going to use, no, the area, no, here in the shear diagram. Okay, so let's say at this point, class, we are going to use this area 1. Okay, at this point, so there's an area here, area 2. And then this triangle will be the area 3. And then this rectangle will be the area 4. And this rectangle will be the area 5. Okay, so here, class, no, we can see here that the shear diagram, okay, in this shear diagram, class, okay, so the graph, class, passes through the x-axis at this point. So we have to determine this distance, no? So let's say this is distance x. So if this is distance x, this since this is 4 feet, class, okay, so meaning to say, this remaining distance, it will just be 4 minus x. Okay, so 4 minus x, this will be this distance. Okay, so class, we can solve for the value of x, no, by using proportion of these two triangles. Okay, so these are similar triangles. This is smaller triangle and this larger triangle, no. So these are similar triangles. Therefore, we can use proportion here, okay, to solve for x. Okay, so for the proportion here, class, so the height of the larger triangle, which is 300 pound, so it will just be equal over ulit. Okay, again, so the height of the larger triangle, which is 300, okay, disregard the negative sign, over its base, which is 4 minus x, it will just be equal to the height of the smaller triangle over the base of the smaller triangle. That's why here it will become 100 over x is equal to 300 over 4 minus x. Okay, so you can use your calculator, no, to solve for the value of x. Okay, so we can interchange the numerators here and the denominator, so that the calculator uh, will be able to give the answer easier or faster. Okay, so it can be x over 100 is equal to 4 minus x over 300. Okay, so the answer here, class, is 1. Okay, so you have to check if this value of x is logical. So in this case, class, no, so since this is 4 feet, okay, and this is the distance x, so we can say that our answer is logical naman, no? So this can really be 1, right? Okay, so therefore 4 minus x equal to 3. Okay, so from here, class, now we can now start solving for the moment at each point. So we will start, no, at x equal to 0. Okay, so at this point, class, again, there's no applied couple or moment here. There's also no reaction moment here. So the moment here will just be 0. Okay, so for the next point, that will be at this point. So this is x equal to 2. No, so at distance x equal to 2, class, so that will be at this point. So class, the moment at this point, class, will just be the area, no, in this segment. Okay, so the area here, class. Okay, so this is a triangle. Okay, so this is a triangle. Okay, and this is also below the x-axis, so it will be negative, this area. Okay, so class, the moment, class, will just be the area 1. Okay, since this is below the x-axis, class, so this will be negative here. Okay, so this is a triangle with base. What is its base? So the base is 2 feet, and its height, class, will be 200. Again, disregard the negative sign, here. Okay, so the area here, class, therefore, will be negative 1/2 base times height, so that will be negative 1/2 times 200 times 2. Okay, so class, therefore, the moment at x equal to 2 is negative 200 pound-feet. Now, at the next point, which is at this point, so this is, its distance, class, from the left is 2 plus x. So that will be 2 plus 1. No, the value of x is 1. So therefore, at this point, this is 3 meters from the left. Okay, so at distance 3 meters from the left, class. Okay, so the moment here, okay, will just be the previous moment, and then we are going to sum up the area in this segment, which is area 2. So the moment here will be negative 200. So this area, class, this area 2 is above the x-axis, so it will be positive, no? That's why it will be negative 200 plus a2 here. Okay, so the area 2 here, class, this is a triangle. So the base of the triangle is x, which is 1. The value of this is 1. And then its height is 100. Therefore, the moment here will become negative 200 plus 1/2 times 100 times 1. So the moment here will be negative 150 pound-feet. Okay. Okay, now proceeding to the next point. So the next point will be at this point. So this is 7 meters now from the left. No, 6 meters rather. So this is 6 meters from the left. So at x equal to 6, class, okay, the moment at this point, class, will just be this previous moment. Okay, and then we are going to sum up the area, no, at this segment. Okay, so the area in this segment, class, is the area 3. So therefore, class, the moment at x equal to 6, that is negative 150 minus area 3. So this is below the x-axis, that's why it's negative here. Okay, so the area of this triangle, class, is 1/2 base times height. So its base is 4 minus x, which is 3. And then its height will be 300. Okay, so therefore, the moment here will become negative 150 minus 1/2, 300 times 3. So the moment here, class, will be negative 600 pound-feet. Okay, now for the next point, class, or segment, will be at this segment. So class, take note here that there's a couple here, ha? So we should solve the moment at this point. So this point is 2 plus 4 plus 1. So that will be 7, no? So this is 7 meters. No, 7 meters from the left. Okay, so at x equal to 7, class, the moment will be the previous moment. And then we are going to sum up the area at this segment, which is A sub 4. Okay, but class here, this area is below the x-axis, so it will be negative. Okay, so this will become negative 600 minus area 4. Okay, so for area 4, class, this is rectangle. So this is just base times height, wherein its base is 1 and its height is 300. Okay, so therefore, the moment here will become negative 600 minus 300 times 1. So the moment here is negative 900 pound-feet. Okay, so class, at this same point, no, you can see that there's a 1,200 pound applied couple here. Okay, so class, this negative 900 pound-feet, no, so due to this applied couple, class, no, it will change to negative 900. Okay, and then we're going to sum up, no, this applied couple. Okay, so class, this applied couple is clockwise. Okay, so the sign convention here will be positive. Okay, so therefore, at x equal to 7, the moment will become negative 900 plus 1,200. Okay, so the moment here, class, will become 300 pound-feet. Okay, so lastly, class, at this point, so that will be at this point, no? Okay, so the moment here, class, supposedly it should be 0, ha? So we have to check that. Okay, so at x equal to 8, class, no, so the moment will just be 300 minus area 5. Okay, so this is our area 5. This is below the x-axis, so it will be negative here. So the area, class, or the area 5, class, is 300. The height is 300, and then the base is 1. Okay, that's why it will become 300 minus 300 times 1 here. So the moment here, class, will just be 0. So obviously, it should really be 0, ha? Since at this point, there's no applied couple and there's no reaction moment. Okay, so we are now going to plot these values in the moment diagram. Okay, so plotting the values of the moment, no, that we computed from the previous slide. Okay, so class, at x equal to 0, the moment is 0. Okay, at x equal to 2, that will be at this point. No, the moment here, class, is negative 200. So this is negative, so this will be plotted below the x-axis. So negative 200 is here. And then at this point, so this is at x is equal to 4, no? 3. Since this is 2 and this value or this distance is 1, no? So this will be 1 plus 2. So at x equal to 3, class, the moment that we computed is negative 150. Okay, so negative 150 will be at this point. Okay, and then the next one at this point, so this is x equal to 6. Okay, the moment here, class, is negative 600, so it will be plotted here at this point. And then at this point, class, no, the moment at x equal to 7 is negative 900, so it will be plotted at this point. Okay, and then at this same point, class, no, due to the applied couple here, this moment, okay, it will be changed to 300. It will become 300. Okay, so positive 300, no, so it will be plotted above the x-axis. Okay, and then from here, class, no, at this point, no, so we know that the moment here is 0. Okay, okay, so we are going to connect the points here, class. So from this point to this point, so from the shear diagram, this is a triangle. Okay, so the moment here, class, will be parabolic. No, so the curve here will be concave downward, no, since the shear here is sloping down. So sloping down, the curve should be side, so it should be concave downward. Okay. Also here, class, no, from this point up to this point, so we are going to connect this also. So the shear here, class, is a triangle. Okay, so this should be parabolic. This curve should be parabolic. And since the shear is sloping down, so this curve should be concave downward. That's why it's concave downward here. Okay, same here from this point up to this point plus. Okay, the shear here is a triangle, so the curve here is parabolic. And then since the shear is sloping down, so it should be concave downward. Okay. Okay. So from here naman class up to this point, from this point up to this point. Okay. So class, this is constant and this is rectangle, no? So class here, the shear, the moment rather should be ano no, a triangle. So it should be connected by a straight line only, ha? So this point up to this point, so this is just a straight line. Okay, sloping down. Okay. So here there's a change in moment, so it will go up here. And then from here, this is just a rectangle, no? So the moment will become triangle, ha? Okay, so the points here from here to here will just be straight line. Okay, so this will now be the shear and moment diagram class, ha, for this problem. So for the maximum shear force from the shear diagram, so as we can see here class, the maximum here class is negative 300. Right? So the maximum shear class is negative 300 pound. Now, for the maximum moment, as we can see here class from the moment diagram, the maximum moment here class is this moment. So this is negative 900 pound feet. No? So this is the maximum moment. Okay, so the continuation of this discussion will be shown in the next video.